This is the dragon game I'm working on. In the previous video, I showcased the locomotion system. In this video, I will show the animation logic that I added on top. And just like last time, I will be explaining my solution, but this isn't a follow-along tutorial, and prior Unreal Engine 5 knowledge is needed to understand what I'm talking about. I have included the resources which taught me how to put together this animation logic in the description. This dragon model came with its own cute animation sequences, so I already had all the assets. Next, I created an animation blueprint and attached it to my character. I did this in the character blueprint, in the viewport, by selecting the mesh, and in the details panel I scrolled down to the animation section and I set the anim class property to my animation blueprint. The animation blueprint has two parts, the event graph and the animation graph. The event graph is similar to the character blueprint event graph, as in you can compute values and put them in variables. The animation graph contains my animations and their transition logic that binds them together. See the tutorials in the description to learn the basics of animation blueprints and animation graphs. In my animation blueprint event graph, I left the default third-person character code unchanged. So that means that in the initialization event, it saves the references to my dragon character so that I can access its variables later. With every animation update, it checks that the character exists in the world before doing anything. If it exists, then several things happen which I've organized with a sequence node. The code for setting the speed, should move, and is falling is the default code from the third-person character, so there is nothing new here. After that, I have a bunch of logic in the rest of the sequence pins where I compute various variables needed for my animations. Things like character rotation and the locomotion environment. When I was developing this, I would first create the animation logic in the animation graph and then compute the necessary variables in the event graph. So now I'm going to switch over to the animation graph, and I will explain the rest of the event graph later, together with its associated animation. In my animation graph, each locomotion type has its own animation subgraph inside each of these nodes called state machines. Otherwise, it quickly becomes a mess of states and transitions. Please check the tutorials in the description if you are not familiar with state machines. I bring all these subgraphs together in this node called blend poses by int, and my int is this variable called envint, which represents the locomotion environment type. So if I'm running on the ground, envint will be 0, and this will play the ground locomotion animation graph. If I'm flying through the air, envint will be 3, and it will play the air locomotion animation graph. You can set the blend times to determine how quickly to transition between locomotion types in seconds. If the time is too short, the animations will be snappy, and that's not what I want. I will talk about this default node later. It is used in playing animation montages, and right now we are focusing on the animation graphs. You can delete this node if you are not using animation montages. So where am I getting this envint variable from? In the animation blueprint animation graph, you can access the variables that you create in the animation blueprint event graph, which are very useful in choosing which animation to play. In turn, in the animation blueprint event graph, you can access variables from the character blueprint event graph. That's why we saved the reference to the dragon character when the animation blueprint initialized. So let's switch back to our animation blueprint event graph. One of the pins in the sequence in the update animation event calculates the environment type and saves it to envint. This happens every tick, so the animations are quick to switch if my dragon is flying, then swimming, then running, then flying again. I get the locomotion environment variable from the character blueprint, and I map it to an integer. The original locomotion environment is an enum, so I associate each option with a number. Next, let's dive into each locomotion animation graph. In my ground locomotion state machine, I have four states: idling, moving, falling, and landing. When I'm on the ground and not moving, I want to see different idling animations at random. To do this, I have this separate state just for idling, and inside it, I have a random sequence player with a collection of all my 6 idling animations. In sequence, I select the animation sequence that I want to play. The higher the field chance to play is set to, the more likely that animation will get picked to play. In my case, I want to see more of the first 2 animations and less of the others, so I set the chance to play to 3 for those 2 and I left it at 1 for the others. Min loop count refers to the minimum number of loops it will play once the animation is selected. The default is 0, which will play the animation once, hence never looping. But for my first 2 idling animations, I set it to 10, because I want my dragon to mostly be standing still, but sometimes look around or scratch its head. In my ground movement state, I handle the running animations. I made a blend space which takes in the speed and left-right direction of my dragon. In the blend space, my speed ranges from 0 to 800 on the x-axis, and my turn left-right ranges from -100 to 100 on the y-axis. Because I am handling idleness in a separate state, I could make the speed range start at a higher value, such as 50, but right now it is irrelevant. My max ground speed is 800, so I placed the running animations there. I have walking and trotting animations, but right now I do not support varying speeds, so I left them out. The values in the y-axis of the character rotation go beyond 100 and -100. But to my blend space, it doesn't matter, because once it hits 100, it can turn more to the left than it already has. I am getting the speed and turning values from variables that I created in my animation blueprint event graph. The velocity is a vector, so to get the speed out of it, I get its length. And to figure out if I'm turning left or right, I use the y-coordinate from the character rotation vector variable. To compute the character rotation, in the update animation event, I get the actor rotation of my dragon character, and then I unrotate it according to its velocity. The fall loop state just has the falling animation set to loop in the details panel. Likewise, the land state has the landing animation, but its loop setting is set to false because when landing, you only flap your wings and set your feet on the ground once. Some of these transitions I got from the default third player character animation graph, and I modified the rest. They come with the variables is falling and should move calculated in the event graph. I transition from idle to movement if I'm not falling and I should move. I transition from movement to idling if I am not falling and I shouldn't move. I go from movement to falling if is falling is set to true. Likewise, going from idling to falling happens if is falling is set to true. I can only land if I've been falling previously, so that is why the land state can only be reached from the fall loop state, and that happens if is falling is set to false. Once I land, I am on the ground either idling or running. Between land and idle, and land and movement, I have 2 transitions each in the same direction. One has the obvious logic based on the should move variable. The other doesn't have any logic and instead checks this box called automatic rule based on sequence player in state. I don't understand how this works, but without it I never get to see my landing animation because it quickly goes through it into either idling or movement. You can find this esoteric transition in the third player animation graph. My water surface animation subgraph is very simple. I have one state which includes both idling and movement. I only have one swimming idling animation, so I don't need a separate state for it. In the movement state, I have one blend space, similar to my ground movement blend space. It takes in the same variables as we saw before, the speed of my dragon and the character rotation y-axis to determine if it's looking left or right or straight, in order to play the correct animation blend. The value ranges of the speed and left-right direction are the same as for ground movement. At speed 0, we play the idle swimming animation. At speed 800, we play the swimming fast animation. Left is at 100 and right is at minus 100 on the y-axis of the blend space. My underwater animation subgraph is similar to the water surface subgraph. I have one state for both idling and movement. I have one blend space which takes the same speed and character rotation variables. The only differences are the animations that I'm playing, but all the other values are exactly the same. My air locomotion subgraph is simple, but it took me a while to figure out the correct setup. I have a state for idling and a state for moving. The transitions are intuitive. I go from idle to movement if I should be moving, and I go from movement to idle if I should not be moving. In my idling state, I am playing the flying idle animation on repeat. My movement state is interesting, however. I am using a blend space with two variables, flying left-right for turning left-right, and normalized pitch angle for knowing when I'm flying upwards, downwards, or straight. My flying blend space consists of only moving animations, so there are no idling animations, unlike the other blend spaces we've seen. The y-axis has the normalized pitch angle, which I've mapped to a range between 100, which is flying upwards, and minus 100, which is flying downwards. The x-axis is turning left and right. When my dragon is flying upwards, I want it to flap its wings to show the effort of going against gravity. When flying straight, I want the wings to be straight, gliding with its existing speed. And the more I point downwards, I want the wings to fold more to show that it's increasing its speed, just like a bird diving from the sky. The math to calculate this normalized pitch angle was fun to come up with. I am using the word normalized incorrectly here. What I mean is that I am taking the raw pitch angle and I am mapping it to the minus 100 and 100 interval. I start by taking the pitch of the camera rotation. This has the values of the right two quadrants of the trigonometric circle. So 90 if I am looking all the way up, 0 or 360 if I'm looking straight ahead, and 270 if I'm looking down. So I want the upper quadrant to have values from 0 to 100, where 100 represents 90 degrees, and the lower quadrant to have values from 0 to minus 100, where minus 100 represents 270 degrees. For the upper quadrant, I can just work with the angle values themselves because 0 to 90 is close enough to 0 to 100. It's the lower quadrant that I need to map. To do that, I first divide the angle by 90. This now gives me 360 divided by 90 is 4 when I look forward, and 270 divided by 90 is 3 when I look down. I then subtract 4 from this, so now I have 0 when I look forward and minus 1 when I look down. I then multiply this by 100 to get 0 when I look forward and minus 100 when I look all the way down. So now the pitch angle maps to my blend space correctly. When I'm flying and I turn left and right, my dragon rotates to match the direction it's going in. This makes for a better flying experience and a more natural feel in the dragon's movement. This rotation happens on the x-axis and it's called the roll angle. To do this, I calculate the rotation every tick and save it in a variable. I want my rotation value to be between minus 50 and 50. I found these numbers by trying them on my dragon to see at which tilt it looked more natural. The raw numbers that I get from unrotating the control rotation tell me how quickly I'm turning left and right, and they are well outside the minus 50-50 range. Unlike the pitch angle, I don't care to map all possible raw values to my interval. I care that the speed with which I turn is reflected in the angle at which my dragon rotates. So if I gently turn left, my dragon will tilt a little, but if I quickly turn left, my dragon will tilt at the max. I printed the unrotated vector values to the screen to get an idea of what values I'm dealing with, and then I trimmed them down by dividing by 5 and subtracting 8. I got these numbers through tweaking to see what felt smoother. After this math, if the value is between -50 and 50, then great, use it. If it's less than -50, just set it to -50, and if it's greater than 50, set it to 50. To actually rotate the dragon, I call set actor rotation. The flying X rotation that we calculated earlier goes into the X-axis, and the pitch of the control rotation goes into the Y-axis. This is so that the dragon rotates with the camera when I look up and down to look like we are flying with the dragon. If I don't do this, we end up seeing its back when the camera looks down and its belly when the camera looks up, and that breaks flying immersion. To make it a smooth rotation, I use a node called RInterp2, which means Rotation Interpolation 2. Interpolation refers to the gradual transition from one value to another. In my case, the starting rotation is my current rotation, and the target rotation is flying X rotation for the X-axis, and the control rotation for the Y-axis. And I set the interpolation speed to 2 seconds, which means that over the span of 2 seconds, the dragon will go from the current rotation to the target rotation. If I make this number smaller, the interpolation will happen faster, and it will be too snappy for my taste. The interpolation effect needs several frames to show up on the screen. So if I call an interpolation node in an event that fires once for 1 frame, I won't see anything because there was only 1 frame to work with. So I want my interpolation node to be in a place in the code where it can get several frames so that I can see the effect. In my case, I only want my dragon to rotate when I'm flying and moving. I don't want it to execute if I'm idling in the air. So the best place to set this rotation is in the flying movement event code. The rotation will happen as long as I hold W pressed to fly somewhere. And it will have enough frames in a row in which this code activates so that I can see my dragon rotate when I move the mouse left and right to fly in that direction. I use the same rotation code in the underwater movement event because it looks pleasant. Let's go back to the air movement state from my animation graph, because I calculate flying left-right differently than for the other locomotion types. In the animation blueprint event graph, in the animation update event, one of the pins calculates this variable every tick. I am doing a rotation interpolation using the flying X rotation variable from the character blueprint. This is because plugging in the flying X rotation directly into the blend space looked choppy for some reason. In the air movement blend space, I also moved the left-right animations on the values -50 and 50 of the grid instead of -100 and 100 in order to match the value range of the flying X rotation variable. Setting the rotation like this manually creates some bugs. When I fly or swim underwater and I turn, my dragon tilts as expected. But if I stop moving, my dragon will remain tilted while playing the idling animation, and this is not what we want. Another bug is with transitions between locomotion types. If I'm flying and I turn and my dragon tilts, and I enter the water, my dragon will remain tilted while it's swimming on the surface. This issue happens both on the X and Y axis, since we set them both manually while swimming underwater and flying. Same issue happens if I'm swimming underwater and I turn and tilt and I stop swimming underwater and float to the surface. The dragon will retain its tilted angle both on the X and Y axis. Remember that air, water surface, and underwater locomotion types all use the flying movement mode under the hood, so Unreal doesn't step in to fix the rotation by default with gravity and whatnot. This issue doesn't happen with transitions to ground locomotion because it is using the walking movement mode under the hood, which causes Unreal to apply its own physics system and correct the angle. So to fix these bugs, we just need to reset the dragon's rotation to neutral in the following cases. 1. When idling and locomotion type is air or underwater or water surface. And 2. During water surface movement. This one is needed because I can be flying, I tilt, dive into the water, and keep moving, and because I never idled, my tilt from flying is still kept. Once I stop moving, my rotation fixes itself. So because of this, I need to reset the rotation during water surface movement too. I reset the rotation for both of these cases in the event tick because I want enough frames to call this code in a row so that I can see the interpolation. For animations that only play once, I use animation montages. See the tutorial links in the description to learn about animation montages if you're not familiar with them. To create my animation montages, I right-clicked on the animation sequences that I wanted and created animation montages out of them. I use animation montages for all my locomotion environment transition animations. So that is taking off from ground to air, entering the water, and jumping. The only odd one out is landing. As I said earlier, that one I left in the animation graph because Unreal can detect when I hit the ground and play the animation much better than I can do it manually in code. For the other three, it is easy to identify the place in code where they should play and add a play anim montage node there. Jumping is straightforward. In the jump event, I play the jumping animation montage, and that's it. For taking off, I go to the takeoff event. If I try to just play the taking off animation, I create this bug where if I'm running, then jump, and then quickly start flying, my jump animation will still be playing, and then the takeoff animation starts to play while I'm in the air, which looks wrong. So when the takeoff event starts, I check if I was previously walking. If this is true, then it means I am on the ground and I should play the takeoff animation. If I am not walking, then I stop the jumping animation montage. This works because when you jump, Unreal sets you to falling movement mode. If no jumping animation montage is playing, then this code doesn't do anything. For entering the water, I go to my enter water code and I play the corresponding animation montage. Straightforward. I did find a bug where the slope of the ground next to the water sometimes has a weird angle, which causes me to enter the water and then quickly exit it. This causes the enter water animation to play while I'm walking on the ground, and it looks like I'm diving through the ground. I don't want this, so in the code, which detects when I exit the water, I stop the enter water animation montage from playing, similar to how I stop the jump animation when I take off. And that's everything I did to add animations to my dragon.